In Unit 9, Section 6, we're going to look at exponential growth and decay, which is really an application of these exponential functions, and then sometimes using logarithms to solve them, or natural logs if you're dealing with base e. So this kind of ties everything together that we've been talking about with exponential functions and logarithms. Now, in these, and I have some of this stuff on your blue reference sheet, we've got some things that are going to stand for certain things when you're dealing with these word problems. So if we look right here, y will always be the ending amount. A will always be the initial amount or starting amount. R is going to be the rate of increase or decrease. Okay, and that's written as a decimal, so it's going to be given as a percentage. Again, to get rid of the percentage sign, you got to move the decimal 2 places to the left. And a lot of we see lots of mistakes with these, so make sure you're entering that correctly as a decimal. And then T stands for time. Most of the time, that's going to be in years, but it could be months, it could be days, could be hours, so some amount of time. Okay, so these are the general equations that I have on your blue reference sheet down here. Growth, and we've got two forms. Some of them deal with base e, and that's usually when it's a little more scientific. And then the growth is when we have y, the ending amount, equals a times 1 plus r, okay, as a decimal, to the power of t. Okay, so that number inside there that's raised to the power of t is going to be bigger than 1 because you're adding the rate of increase. Okay, and the only thing that's different on the decay for that one is 1 minus r inside there, which is going to cause it to be less than 1, which again means it's decay. And then the only difference between the ones that have the base e in them, again, y is ending amount, a is initial, we have base e to the negative kt power or to the positive if it's growth. All right, so and look at an example here. We'll do number 1 here, which is the first one. So let's make this a little bit bigger. It said a radioisotope is used as a power of source for a satellite. The power output P, which is in watts, is given by P equals 50 times e to the, and that's a negative sign right there, negative, and then t over 250, where t is time in days. We need to find the power after 100 days. Okay, so you got to kind of think about what information you're given. You're given the amount of days, which in this case we know what t is, the time. We're trying to find the power, which is p in the equation. Okay, so all we really need to do for this one's not going to involve having to use any type of logarithm. In this case, we're dealing with base e, but we don't have to do, because we're not trying to solve for an exponent that's in, solve for a variable that's up in an exponent. We're trying to find p. So I'm going to have down here that p is equal to 50 times e to the negative, and in for t right there, we're going to put 100, so it's 100 over 250 up in the exponent. Okay, which if we go through and do that, we've got, I'll change colors here, p equals 50 times e, and if you take 100 divided by 250, that's negative 0.4 power. So really on the calculator here, all we need to do is we need to do e, and I would do this first, take e, use that e button that we dealt with in section 5, to the negative 0.4 power, and you're going to hit your times symbol, and you're going to multiply it times 50, and that's going to give you P, which is the power output in watts. And if you go ahead and do that, and we'll round off to the nearest tenth of a watt. It doesn't tell us where to round, but we get about 33.5 watts. Now again, that's taking e to the negative 0.4 power, multiplying it by p. Let's go